Okay, lecture 5. This is when things start getting fun and exciting. And I know you're asking yourself, how could this possibly get to be more fun than we're already having? Well, I'm glad you asked that question. It's good of you that you asked. I will show you in a minute. Now that we have moment distribution figured out, you're back up to speed on it, wherever you were before, now we're all on the same page. Now we can start looking at multiple spans. And that's where things get to be fun. So, stresses in the indeterminate beam. We know that in cast-in-place concrete, we create T-beams out of a floor system. We're really just creating this section. There's nothing magical. There's no line actually on the floor that's there. The code tells us that we can use an effective flange width, and hopefully you learned that in reinforced concrete. We're allowed to get our own flange width, and this flange width, hopefully you learned, let's use real. Is 16 that's not pretty. 16 flange thicknesses plus BW, or it's 8 T on each side. So we start there. We've got 14-inch wide beam, 30 inches deep. We're going to make this T-beam out of it. So the flange width, 16T plus BW, is 110 inches, or it's equal to the spacing of the beam, the smaller of the two. If your beam flanges start overlapping, because your beams are too close to each other, then you can't use more than half of the distance to the other beam's flange. So that makes sense. In this case, our flange is 110 inches. I bring this up because you will do that in your project. So I want to remind you that in your project, I'm going to give you a floor system and some beam spacing, and you will figure out the section properties of that beam. So your project's still a ways away, but this is what you will do. You will calculate the area of that section, Y top, Y bottom, the moment of inertia, and the section modulus to the top and to the bottom. So we did that in homework number 1. You will do all these calculations again in the project. So we're practicing right now. Very important to remember that we are working with service stresses. When we are calculating stresses in concrete to meet the allowable section of the code, allowable stress requirements of the code, we are using service loading. That means it's not the factored loading that you did in reinforced concrete. There is no 1.2 times the dead, no 1.6 times the life. We will get to that. Pre-stressed concrete's required to go through that whole process too. But we have an earlier process, and I've said pre-stressed concrete's kind of burdened with these 2 different designs that we have to do. So the first one is just based upon the everyday load that we will allow day in, day out, morning, night. This beam has 7 tendons, and for the moment, at the end of this lecture, I'm going to talk about where this 26.6 kips per tendon comes from. But for right now, just take that as a given, which gives us 186.2 kips of force, tension force in these tendons. 45-foot span, 40-foot span. For all practical purposes, the closest we can get in a beam to the edge of the beam, we take the tendon center of gravity, is about 4 inches. Anything less than that, the fact that we have 1.5 inches of cover to stirrups, which we're not showing yet, we'll get to that towards the end of the course, but there are stirrups in there. There's a 1.5-inch cover. And then our tendons, these 7 tendons are actually grouped. They're actually, now they may not be in one group, and they probably won't be, but this would probably be in 2 groups, one of 3, one of 4. But the point is that we're taking the center of gravity of that group. So when you're calculating the distance to the centroid of all that group of tendons, and you take all those other things into consideration, 4 inches is about as close as we're ever going to get. So in this course, that's where we'll be when we want to fully drape. Notice that the span is shorter. We don't have the full drape in that particular span. And by the way, I am setting you up for homework number 3, which to me, homework number 3 and homework number 5 are the 2 most important homework assignments that I'm going to give you. And so right now, this is the most important assignment that we're building up to, homework number 3. So by this point, hopefully you understand, we are not going to use any mathematical methods to do this. I hope I impressed upon you that it quickly becomes almost impossible to do the mathematical method. We don't need it. We've got the equivalent load method. It's better than anything. So that's what we will use from this point forward, the rest of the course, the rest of your life, the project. We're never going to abandon it. So what we are trying to do here is to calculate the A dimension. Remember, that's the maximum drape on a line drawn from the high point, or the anchorage point here, to the high point here, 2 ends of that particular span. Draw this line, and we're trying to determine what that drape is. So we know this is 4 inches, so the beam was 30 inches deep, minus that 4 inches is 26 inches. So the way I like to do this calculation, keeps me out of trouble, is I start with that dimension from the very top, that 26 inches, minus 8 inches plus 4 inches divided by 2. So I'm measuring the distance, I'm subtracting that distance. So A in this span, in this example, is 20 inches. Remember that 8 FA over L squared is our equivalent load, so we'll calculate that. We have 1.23 kips per foot upward happening in this span. Now in the next span, the span itself is different, CGS is different. Approach it the same way. The distance from the top is 23 inches. Subtract that same 8 inches plus 4 inches. We will almost always, if not always, anchor the post-tensioning at the center of gravity of the beam. So that center of gravity of the beam, that 8 inches, we actually calculated right here. So again, I'm setting you up for the project. That's how you're going to approach your beam design. So in this span, we go through the same process. We get A to be 17 inches, and even though we have less drape, we actually have more upward force. And one thing to notice here is that as the spans get shorter, it's easy, well, you will be balancing more load. These are also called balance loads, but it's this number is squared. So as that's getting smaller, this number is going to go up, even if the drape isn't a full drape. When I showed you that PowerPoint presentation and that concrete was exploding up, that was what was happening there. This span had become very short, and this drape, I believe they were draping as much as they could. That's what exploded that concrete up in the air. So because our applied loads are uniform distributed load of 2 kips per foot, and we have an upward load that's also an evenly distributed uniform load, we can just offset those. We can just find the net load on the concrete only. if these weren't the same exact load patterns, if this had point loads in it, or we had a trapezoidal type of load, or some, or the harped tendons created a point load, then we couldn't do this. But because both loads are uniform loads in both spans, we can figure out what the net load is. In this case, on span AB, the net load is 0.77 kips per foot, and span AB is 0.68 kips per foot. So I can't impress upon you enough that this is the concrete only. This isn't statics. We have, just like we did in the simply supported beam, we took out the tendon diagram. That's hovering off to the side. Remember that the upward loads that the tendon's creating on the concrete are equally and oppositely balanced by the concrete pushing down on the tendons. So they really offset each other. That's the correct static approach to this. This would be the 2.0 kips per foot. That's statically correct. If you did that moment distribution, reaction, shear diagram, that's what statics says is happening. We have fictitiously put the upward balance load on the concrete and ignored the fact that the concrete is doing the same thing back to the tendon. So we're only including about half, almost exactly half, of what is happening in pre-stressed concrete. So in this pre-stressed concrete beam. So the concrete only thinks that these are the loads on it. Not statically correct, but very useful for calculating the stresses in the concrete. So quickly, we're going to do a moment distribution. Notice that I've got KBA and KBC are both 3 EI over L because the far end of those is truly a pin at the end of the beam, meaning that moment will be 0 and that moment will be 0. Therefore, the stiffness on this side, I can utilize that 3 EI over L. Now in this particular case, it wouldn't matter if I used 4 EI over L or any number because the 3's are going to cancel each other in this. But if you had a 3-span beam, you couldn't make the mistake and still get the right answer. So just want to be anatomically correct as we go through this. 3 EI over L is the correct stiffness term for the moment distribution that we're going to do. The 3's cancel, the EI's cancel. We have this equation that results in 47.1% of any unbalanced load is going to go to this side. And the remainder, 52.9%, will go to this side of the beam. This is how I want you to approach this. Your fixed end moments are always WL squared over 12. It's easiest if you just think in those terms. So we have a fixed end moment, WL squared over 12, based upon the net load in span 1, and we have a fixed end moment based upon the net load in span 2. 130 foot kips and 90.7. Since this is a prismatic member, EI remains constant. We have no rigid zones. The carryover factor is 0.5. Using the right hand rule, I can put on, remember this beam needs to be held in fixity going this way, so my thumb is coming up at me, so that's a plus. On the opposite end of the beam, I'm trying to hold that beam from rotating, and it causes me to have to put a clockwise moment with my right hand. My thumb is going away from me. That's a negative. Same thing on this side. Same concept. So the first step I always take, I know that this is going to be 0, so I apply a negative 130 here and a positive 90 here. I get both of those joints to 0. They each carry over 0.5 to the middle. I add up all of these moments and come up with an unbalanced moment. I change the sign on that unbalanced moment, and I apply 47.1% of that here and 52.9% of that here. And if I've done everything correctly, these will both add up to be the same number, except for a sign difference. So there's no, in a two-span beam with pinned ends, there's no approximation. This is actually an exact solution. So it's as exact as you're going to keep track of in your decimals. So we have a negative moment of 167.2 on the concrete only, drawn to the tension side. That means tension is on top of the beam here. It's tension on the bottom of the beam here. We need to know what the positive moments are, but once we've done the moment distribution, every span is now statically determinate. Remember that. So we will look at span 1. Remember, the net load was 770 pounds per foot. This is the way I like to do this. You can do it any way you'd like. You can sum moments about this point and get that shear and then solve for that shear using statics. That's fine. I've found in my 57 years of existence, most of which being an engineer, that I make the fewest mistakes if I separate out just the vertical distributed load from the moment. So with just the vertical distributed load, and I use WL squared over 2, that would be this shear and this shear. So WL squared over 2, based on 0.77 kips per foot, gives me 17.3 kips on each end. Same number. Then I look at the moment by itself. That moment of 167.2 divided by the length of the beam, the span of that beam, 45 feet, gives me the same number, but the two numbers are going in the opposite directions. So, to be statically and anatomically correct, that moment divided by 45 feet, 3.7 kips, is going down on this side and it's going up on this side. So where I think you don't make mistakes here is that these numbers are always the same as each other, and these numbers are always the same as each other. These numbers, this number subtracts from this, so we get 13.6. On the continuous joint, these two will add to be 21 kips. So you could have done statics in some moments and looked at the vertical forces and gotten the same answer. I like to separate them. Your choice, but to me this is a clear way to go. I do the same thing on this side, and the point is I'm getting to this shear diagram. So I have 13.6 of fictitious reaction. It's not really a reaction, but if we were only looking at what was happening to the concrete, then this would be the case. But we're not. We have separated out all the things that are happening to the tendon. So 13.6, this slope of this diagram is the load. So it's going down 0.77 kips per foot. Every foot this reduces by 0.77. So that tells me that if I want to know where 0 is, 13.6 divided by the slope of that line, 0.77 kips per foot, tells me where the shear diagram has crossed 0. Calculus tells us that where that shear diagram crosses 0, the moment diagram has a 0 tangent. So we've hit a maxima there. We do the same thing over here. For fun, I've started on this side, 17.8 divided by 0.68 kips per foot gives me 26.2 feet from this point. And I'm doing this for a purpose. The maximum positive moment, and remember that the change in moment is equal to the area under the shear diagram. So the change in moment from here to here is the area under that diagram, 1/2 17.7 times 13.6. That's the change in moment. Now, the moment started at 0. The moment we know was 0 at this point. So it turns out that that is the positive moment. It won't always be the case. You have to be careful. I'm trying, as I said, to demonstrate a point here. The change in moment from this point to this point is based upon the area under this shear diagram. But the moment started at 167.2. So the change in moment is the 1/2 26.2 times 17.8. But I have to account for the fact that I started at 167.2. So the positive moment is 66.2. I'll tell you, every year, every school, somebody calculates the area under this and just says that's the positive moment and ends up with a huge positive moment and gets everything from that point forward wrong. Now, I could have taken the area under here where the moment was also started from 0 and gotten that 66.2. Then I wouldn't be demonstrating my point. So we are trying to figure out what the maximum service stresses on this beam are. So the maximum concrete stresses under service loads. The direct compression is the tendon, sum of the tendon force divided by the area of the beam. So that beam has a direct F over A of 187 psi. Remember, that is always negative. In our course, compression is going to be negative. We've chosen that. So tension will be positive. So I'm looking at support B, this 167.2. What are the stresses at the top and the bottom? Well, here's the stress at top. The moment diagram tells me that the M over S portion of this has tension at the top. So M over S top is positive here because I'm calculating a tensile stress minus the 187 KSI. That tells me that the stress in the top of the beam is 0.048 KSI in tension. Now be careful, because you may do this calculation and find out that you're in compression. That happens all the time. If this F over A component is greater than the M over S component, even though the moment diagram is telling you to expect tension, you may get a compressive stress. It's just if F over A is bigger than M over S. In this case, that's not the case. We still have tension on the top. Let's look at what the compression is at the bottom of the beam at that same location. What is it to the bottom side? We're actually looking at what is the compression here. Ooh. So the moment is 167.2. But we know compression's at the bottom because this diagram tells me the tension's at the top. So if I'm looking at the bottom, the M over S bottom portion is negative because it's going to be in compression. The F over A portion is always negative. Therefore, the bottom of the beam is at negative 0.834 KSI in compression. Now you might think, well, I looked at the maximum moment, I'm done. How could anything ever get worse than the maximum moment? Well, that's what I'm here for. The maximum positive moment that you will always have to look at, you're going to have to find the maximum negative moment and the maximum positive moment if you want to find the maximum stresses. We'll talk about why that is in just a second. But so I'm now at 120.4 foot kips. I'm at the maximum moment in span 1. The maximum tension, because the moment diagram tells me that the M over S portion will have tension at the bottom of the beam. So the M over section modulus to the bottom is a positive number here, always negative F over A. So the maximum tension in span 1 is at the bottom of the beam, 279 psi in tension. Maximum compression, again, this diagram, the reason we draw it to the tension side, tells me tension's on the bottom, so by default, compression's at the top. So if I'm going to look at the top of the beam, I know that my M over S top is going to have to be negative. That's a negative stress. That's compression minus F over A. 356 KSI in compression. We don't need to go through the process for this span because that's a smaller positive moment, but we did have to look at the maximum negative moment and the maximum positive moment to get these answers. Now let's look hard at the answers that we got. At the support, the maximum tension, even though the moment was high at 167.2, that was only 0.048 KSI. We had a smaller moment here in the span of 120.4, but we had a maximum tensile stress at that location of 0.279 KSI, substantially higher. So the maximum tension is actually occurring here, not at the maximum moment. Got to be careful with that. In T-beam construction, the difference is that section modulus. The section modulus to the bottom of a beam section modulus to the bottom of the beam is usually going to be, or always in a T-beam, going to be a smaller number than the section modulus to the top. The section modulus to the top, where all the beef of the beam is. So going back and looking at just those section properties, you see that if we have a T-beam, we're substantially greater on the top than we are on the bottom for the section modulus. So that will change your stress calculations. You can't just look at the maximum moment to get the maximum stress. I'm beating a dead horse here, but always look at the maximum negative and the maximum positive moment to get those answers. Okay, so we've calculated the stresses. Now let's compare them to what the code says we can have. In this class, we are always going to be the class U. The U means uncracked. So uncracked in beams and one-way slabs is 7.5 square root F prime C, the rupture modulus of concrete. We have 4,000 psi in this case. A mistake that gets made every year is someone just puts a 4 under here and gets a strange answer, or a 5, or whatever I've given you as the 28-day strength of concrete. Always in ACI, this isn't a Dirk Bondy rule or our book. In ACI, all values under a radical, under the square root sign, have to be in terms of PSI. That's part of the ACI code in the definition. So that number always must be in PSI, even if I give it to you in KSI. To get it to KSI, you divide by 1,000. So this particular case, the code says I am allowed 0.474 KSI in tension. My example only had 279 KSI in tension in span 1 at the bottom. Okay, so we're in the clear. Code also says we have a maximum compressive stress for class U and class T. I told you before, in practice you're not going to worry about this much unless you have a very strange, heavily loaded, strange type of design that you're working on. For us, not so strange, but we're in the academic world, so you're always going to check this. If I ask for checks of allowable flexural stresses, you're doing both tension and compression. So 0.6 F prime C for total load, which means includes the live load. 0.6 times 4 KSI, large number, 2.4 KSI, greater than the 0.84 KSI allowed, easily satisfies the tension or the compression requirements. Now, please don't do this on your homework assignments where I'm asking you to calculate the allowable stresses. I've had a number of people, mainly the ones who don't want to watch the videos, just tell me that 4 KSI was the allowable because I gave them 4 KSI concrete. That is the 28-day compressive strength at breaking. That's when it shatters. You know, we're staying way away from exploding the concrete. So code says we can get as close on 4 KSI concrete. We can get to 2.4 KSI and nothing bad will happen. But please don't tell me that the allowable stress is the full breaking stress. I asked that, and some will anyway. Okay, pre-stress losses. When I was a young man, Cal Poly, and then up again at Berkeley, took this class, 10 weeks Cal Poly, 25 weeks at Berkeley. I've told you, or 15 weeks at Berkeley, a grand total of 25 weeks altogether. And boy, did we spend a lot of time in both classes on pre-stress losses. Now, I would like you to read all this. I'm not going to read it to you. I will basically give you some summaries here. But in the academic world, I think this is one of the reasons people don't like taking this class, is you spend weeks in many classes on calculating these losses. Now, what is a pre-stress loss? Basically, if you stress one end of a long beam, and you only stress that one end, 200 feet away, 240 feet away or so, the stress that you stress to on the left side won't be the stress that you get necessarily on the right side. There is some loss. And then to compound that over time, a series of factors build up that create a decrease in the amount of tension that you first put in the strands. So, where do those losses come from? We're going to cut to the chase here, and I'm going to tell you that most computer programs, you're going to go out to work and you're not going to do any of these calculations to calculate losses. That's what the post-tensioning supplier will do. They will do those calculations. They'll provide them to you based upon your design. You've got some assumed loss that you had to have worked with when you were doing these calculations. Our program and everybody else's program that I know uses either 15 or right around 15 KSI as a long-term loss. No explanation, just that's built into the program because we've all been doing this enough. And if you stick within the parameters of not going too far on a single-ended pull, like not going more than 120 feet on a single-ended pull, or 240 feet on a two-ended pull where you're pulling both sides, first one side, then the other, you should be at 15 KSI or less. You're probably going to be about 12 KSI. That's the typical kind of worst case scenario. So we build in a 15 KSI assumed loss for these things that we're going to talk about. And that's it. That's the extent of kind of what you need to know about losses to actually perform, to actually do a design. Now, we're going to go a little more in depth than that, but we're not going to take weeks. We're not going to take hours. We're going to take minutes and talk about that. Most important thing is that the code says after stressing and seating, you can have 0.7 FPU. Well, FPU is always 270 KSI now. There used to be other strengths of steel when this first started. So the code is written to accept any amount of FPU, but across the board, everything you're ever going to do, most likely in your career, will be based on 270 KSI steel. So that's what we're talking about. Code says when all is said and done, when you've stressed and anchored, you can't be more than a 70% of the breaking strength of the strand. But that's exactly what we're going to stress to. And we don't kid around here. We will take that up, stress it to 0.8 KSI, and then when it locks in and seats, theoretically it's at 0.7 KSI or close enough. But that's what the code says, so that's where our assumption is based upon. That gets us to 189 KSI. I'm telling you that 15 KSI will cover basically everything normal that you're ever going to do in pre-stressed concrete. So we take the 189 KSI minus the 15 KSI loss, and our everyday usable stress in our tendons is 174 KSI. So if that's the case, the force per strand or tendon is 174 times, now remember that the post-tensioning 1/2 inch diameter strand is actually 7 wires all clustered together. So while that diameter may be 1/2 inch, the total area of steel within that 1/2 inch isn't equal to 1/2 inch of steel. So that's why this is not 0.2, which is what it would be if it was truly 1/2 inch. But we call it a 1/2 inch strand or 1/2 inch tendon. And in reality, there's only 0.153 square inches of wire in there. So at 174 KSI times 0.153 square inches, that's not that pretty, but 26.62 kips per strand. Remember, I told you that we're always using 1/2 inch diameter strand. There are cases where we use 0.6, some bridges use some larger, but in building construction, virtually everybody in every situation is using a 1/2 inch diameter strand. So if we're all using a 1/2 inch diameter strand and we're all assuming a 15 KSI loss, and we all stress to 189 KSI, which is what we all do, an anchor, we're all working with 26.62 plus or minus kips per strand every time. So we don't have to, if you just want to remember that number, I remember that number. But every time I tell you, if I tell you the number of strands, you know that the force, the effective force, is 26.62 times that number of strands. By the way, I will, and this confuses people, sometimes write F sub E. That's just kind of known in the industry. The little sub E means effective force. So there could be an original force, there could be a force after losses. Force after losses is considered by most of us the effective force in the strand, meaning force after losses. So sometimes I'll have a sub E in there that's not meant to be the eccentricity. I try to make that a smaller E, so it's not F times E, it's just F sub E. Slightly confusing if you're not 100% sure about what we're talking about. Okay, so what are these losses? Well, remember from strength of materials that any material with a modulus of elasticity, an area under a force given a length, is going to move elastically. It's going to have an elastic deformation. So we're putting large forces, whether or not we stress this side or not, and that's the dead end. Either way, the force is being applied to both ends. I hope that's clear to you. We're stressing this end. This is a dead end anchor. It's not being stressed. It doesn't matter. The force is coming through the tendons. And there's a force here too. Now, if there were no losses whatsoever, the force at this point would be exactly equal to the force at this point. But we have things that cause, there's two different things that happen. Sometimes there's a loss over this distance, and sometimes there's just a loss to the whole system. This elastic shortening is a loss to the entire system. So just due to the large compression in the concrete, we have an elastic deformation. So let's do that better. Do better. That's what my kids tell me. Okay, so just elastically, the member after being stressed is going to shorten. It has to, according to PL over AE. That will cause the tendon to have less stress in it. So the tendon started out this long, and elastic shortening moved it in. So if the tendon is moving in, it's a big rubber band. It's losing some of its force due to that. Okay. That was elastic shortening. Concrete shrinks over time. It's hydrating. It was wet when it first, its first days of its life. Starts shrinking, starts hydrating. That hydration leaves voids in the concrete. Now, in reinforced concrete, we just end up with a whole bunch of cracks throughout the system. Hopefully they're relatively small cracks and we don't see them and they don't stand out that much. In post-tension concrete, we really don't see those same cracks. After we have stressed, we're in such compression on the concrete that the shrinkage is actually causing more volume change. Instead of cracking and having a lot of that shrinkage change in length happening in little tiny pieces that all add up to maybe a half inch or 3/4 inch, the shrinkage portion in pre-stress concrete is all happening at the ends. That just the fact that it's in compression tries not to allow the cracks to develop, and what ends up happening is another movement in from the ends. So we're seeing that those two effects, elastic shortening and shrinkage, are changing the volume, changing the length of the beam somewhat, and that length change is changing the length, the stretched length of the tendon inside. Now, concrete creeps over time. It creeps in the direction that it has compression. So even in flexure, there's a compression side of the beam, and we're aware of that creep deflection. When you learned it, you probably didn't learn about it being horizontal also. But if we put a large axial force in a member, it will creep in that direction over time. So it's not just the shrinkage, it's not just the elastic shortening, but another component of that will be the creep. If we're going to compress the beam over time, it's going to creep axially, and that again is another component that causes this tendon to basically be shorter or less stretched than it was on the first day of its life. Okay, steel relaxation is another thing that happens. This is just a property of all steel. It gets stressed. You really have to be a molecular scientist to understand this one. But apparently the molecules in the steel will reorganize themselves such that they're under less stress. So that creates a relaxation in the steel. The steel itself is just trying to accept this tension that's in it and do the best it can to not feel most of it, or as much of it as it has to. So it's called steel relaxation. And so the steel relaxation will create a part of the loss also. Something called wobble that really only happens to us in post-tension concrete. Call this a wobble effect because we're stressing up and down and up and down. There's actually some horizontal components even though the tendon is unbonded and slipping and sliding in the plastic sheathing and it's greased, it is still exerting some amount of horizontal pressure. We think about the vertical loads, and that's what we're doing our calculations based upon. But there's also a horizontal component to it. And I actually did draw it this way. This is more realistic. In our academic world, we assume that we peak at a point. It's easier to do for our 8FA over L squared, a complete parabola, an actual parabolic number between here and here. In reality, there's a reversal of the tendons. It doesn't change your numbers all that much, but PT Data, our program, allows you to model that effect and get the correct equivalent loads. Not particularly important that we do that in the academic world. You're learning the concepts. We don't have to be as exact as we would be in practice, or we allow the computer to be. So that wobble, that fact that there is some amount, as we stress this tendon, of horizontal resistance to movement, that creates some amount of loss too. So these things are all adding up. There's a frictional component. As much as we try to grease and sheathe and make that tendon or that strand slip and slide inside that plastic, there's still some friction. We can't get rid of all of it. And the longer the beam is, the more friction we're going to have. So friction is another reason that we're not going to stick with and have as much force as the jacking force read on the day it was stressed. And then finally we have wedge seating, which, if you recall that hydraulic jack pulling back, it has to pull back a little farther than it wants to allow the wedges to be placed in. The wedges then go in and the jack slides back a little bit. That engages the wedges in that anchor, but that process alone, just the seating of those anchors, actually decreases the stress slightly just due to that seating from the maximum jack stress that it was stressed to. So I hope that's clear. Hope you can understand that. The bottom line is you have these effects, and they all add up to to 15 KSI. Most likely they're less. Most of the results that get sent to us are somewhere in the 9 to 12 KSI loss range. That's because we stick within the parameters of that PTI recommends for length of strand, single-ended pull, double-ended pull. So the fact that our program builds in a 15 KSI loss, we're slightly conservative. We're going to have a little more force in our tendons, than we may think. Pretensioned members have losses too. They are a little bit different. They experience all the same losses, but they don't have the friction loss because they are not in a greased and sheathed plastic environment. They really don't have the wobble because most of the time the precast members have straight tendons, straight strands. They may harp a little bit, but there's not the wobble effect that post-tensioning will get by going up and down. And remember, precast is always simply supported. So it's all that exciting activity is happening, anything they do is happening from one support to another, and that's usually not very long. Whereas in post-tension concrete, you could have a 4-span beam, you could be 200, 300 feet long. And because of the nature, they don't have a seating loss. So they stress their tendons before the concrete ever gets placed. They stress their strands, I should say. That's all seated and all taken care of before we even put the concrete on. So the concrete will then get poured in this mold. These will eventually get cut off, and through bond, they transfer the compression in. but there isn't a seating loss like there is in the post-tension concrete. So, I mean, losses, to be, let's just be blunt here, in precast members, they're shorter, they're single span, they're not going to be that critical. We're a little bit more interested in losses because in cast in place post-tension concrete, we can go much farther. We're draping tendons up and down. Our method of getting force into those tendons requires stressing after the concrete has been placed. So we've got the seating, we've got a few more issues to think about. But all that said, it's not a major deal, and it's not anything you will ever calculate. You can do it if you feel like it, and PTI has some examples, but most of us don't. Most of us will read through an example, watch a presentation once, and that'll be it. We'll remember, all you got to really remember is 15 KSI. Okay, so I know it says end of lecture 5, but we're not entirely done with lecture 5. Okay, for one reason or another, I have brought up that skit most of the years that I have taught. And I'll explain to you why. Unfortunately, you'll probably never watch that skit again without thinking about what I'm going to tell you that I think about when I watch that. But a few things, this is one of those things that I use on tests to see who's watching the videos. So part of this is just to give those of you still watching 5 easy points. I don't know what I'm going to test you on, what year this is, but anything I talk about is fair game. So Will Ferrell was an SNL cast member from 1995 to 2002. When he was done, most of you either probably weren't born or just barely born. And I will tell you something that you probably have not heard from anybody. He wasn't considered very funny. When he was on SNL at the time, those of us actually enjoyed watching the show, he was an awkward guy. His skits didn't strike you as really funny, and most people, and I dabble in comedy myself, so I know funny, and his were awkward. His skits were made you feel a little uncomfortable. And, I just don't ever think he was a particularly successful SNL member. And then he went out and started making these incredibly successful movies. And kind of the next generation came along, really appreciated his movies, and then came back and started watching his skits. And all of a sudden, his skits seemed hilarious from Saturday Night Live. But nobody watching them originally at the time thought they were all that funny. But like I said, it's maybe a generational thing, but he was just a little before his time, I guess. But now, that skit that you just watched was done in 2000, probably pretty well before most of you were born. And it wasn't particularly popular. I liked it because, again, I appreciate actual comedy and know it when I see it. And I remember watching this late one night, just some reruns, and this came on. And I remember thinking, and this is where I will burden you the rest of your life, I remember thinking, that's how most engineers are. It's always more. It's all, we're trying to solve a problem, and the only way we know how to solve that problem is to put more of something in. And I'm thinking more cowbell. That's a kind of an overriding theme for structural engineers in general. We want more cowbell. In pre-stressed concrete, you're going to do this homework assignment number 3. It's going to be the only time where you are actually using less of something to solve a problem. So we, in post-tension concrete, are thinking in terms of less cowbell, while the rest of the engineering world, it's more cowbell for them. If your shear is not working, you need more area, so more of that. If your bending stress is not working or your flexural strength isn't working, more section modulus, plastic section modulus, elastic section modulus. Axially, your column's not working, you need more area. So when we are presented with a problem, our initial instinct is always to provide more of something to solve that problem. And that's what the vast majority of the world does in post-tension concrete. And that's their big mistake, to be honest with you. A stress, the computer will tell you that a flexural stress is not working at some point in the beam or slab, and the young person who's never had this class will put more tendons in. Just start upping the force in the computer until the computer says it all works, because we have a more cowbell philosophy. Your homework number 3 is designed to get you to think in terms of less cowbell. You are actually going to take something that doesn't work. I haven't done your homework yet. I haven't made it up, but I always make up the same type of thing. I've never given the same homework problem twice, ever. Never given the same test problem twice. I know how to make up these things and have them always be different. But this part will always be the same. I will give you something that violates the ACI flexural stress somewhere in the beam. Then I'm going to give you 2 methods of reducing something. First, it will be the drape, and secondly, it will be the number of tendons in one of the bays. And that reduction will actually solve the problem. So I'm telling you what the answer is in homework number 3. So don't spend so much of your time worrying about just getting the numbers right. I've told you what the answer should be. So if you're not getting those answers, there's probably a problem. But I want you to think in bigger terms. I want you to ask yourself why the 2 things that I give you to do, the decrease in drape, decrease in balance load, and then secondly, the reduction in number of tendons, why do both of those actually solve a problem? And remember, it's decreasing. We didn't add anything. We didn't add any cost. We didn't charge ahead like most engineers will do and start adding more force. We're smarter about it. Hopefully, you're leaving this homework assignment understanding a lot more about pre-stressed concrete. But this homework number 3 was the one that kind of opened up all of my eyes to post-tension, the real true power of it. The fact that I can be a participant. I can actually choose force, drape, profile, and try to minimize. It's a game. It's kind of fun. It pays money. They pay me for playing this game, where I get to try to find the combination of whatever it is, drape, number of tendons, that just satisfies the code and results in the least expensive solution. And by the way, the least amount of pre-stressing will also be the least amount of headaches too, because all the other effects, the effects of the building shrinking in, shortening in, pulling on the columns, pulling on the walls, pulling on interior partition walls, those problems are minimized if you minimize the post-tensioning. So the game that gets played, and they pay us for doing it, is to figure out how to satisfy every part of the code, standard of care, and practice while putting in the least amount of pre-stressing in the building. That's the best design, and I almost always ask that question somewhere, particularly at UCLA on the final. But I reserve that to be one of those questions too, where if I want to give you 5 points and you've been watching and listening, that's a way to do it. So there it is. That's the end of lecture number 5. I will see you on lecture number 6.